Okay, hello and welcome everyone. We're delighted that you could join us today, and we truly appreciate you taking the time to be here. Before we begin this webinar, just a few quick notes. All participants will remain muted during the session. This webinar is being recorded, and we'll share the recording with you afterwards. And lastly, if you have any questions at any point, please feel free to drop them in the chat box, and we'll address as many as possible during the question and answer session at the end. And if time runs short, we'll be sure to follow up with email responses. So my name is Paul Montalto, and I serve as one of Kistler's engineers covering the Northeastern United States and Eastern Canada. Today's session will provide a high-level overview of in-process monitoring and control solutions across a variety of industrial production and manufacturing applications. You'll be hearing from several of my colleagues, each sharing expertise in their respective areas. Mike Prisby will start us off with solutions for injection molding production. Kyle Fisher will then cover advanced manufacturing process monitoring systems, including joining systems with servo presses and integrated force sensors, as well as smart single assembly stations. Hernan Hernandez will guide us through some of the most challenging applications requiring leading edge vision inspection technology. And finally, David Allen will introduce solutions for cutting force measurement systems in precision machining, along with high-tech optical sensors for punching, forming, and automation applications. We've got a lot of exciting content ahead, so let's get started. With that, I'm pleased to hand it over to Mike.
Thanks, Paul. We're off to a good start here. We're going to queue up this presentation we have for you. And as you mentioned, any questions, you'll go to the chat box, and we'll see if we could come back at the end of the time here. We basically wanted to introduce you or to cover some information about injection molding and cavity pressure. This is a subject that's fairly popular these days. We want to get into the fact that in the traditional injection molding machine, there is the controls that monitor the machine performance. Is whether you've got an electric machine or a hydraulic machine, you've got feedback that provides the engineer, the user, the different parameters of the process as it's being pushed into the mold, as the process is injecting plastic to the mold. But the true measure of what's going on in the cavity can only be done by measuring the cavity pressure of the plastic as it's flowing in to see that you have a consistent and repeatable process. So the fundamental theory here is that there's sensors in the cavity that will measure the plastic pressure and be able to give you the information in real-time format. And you can make decisions on and or have as evidence or proof of how the process has been performing. Let's start at the beginning with the structure of the sensors. Kistler is a sensor company, and we basically use the piezo technology, which is forming sensors from crystals by cutting different shapes from the crystal in order to get the properties of output from the sensor. Essentially, when crystals have force applied to them, they give off an electrical charge naturally, and it's linear to the amount of force that's being applied to them. So it's a natural born sensor material, quite honestly. And we'll see more of how it works in just a second here. The basic frame or the cylinder of the sensor is a high strength steel such that it protects the crystals from any kind of damage. Inside the sensor, the cross section, you'll see there is no electronics. You just have the crystal cartridge and insulating details to allow that electrical charge to be sent to the connection cable, which will eventually go to an amplifier and a monitor screen so that you can see the pressure output. Essentially, the sensor is mounted in the cavity and senses the plastic flow as the plastic pushes against the tip of the sensor during the filling process. As we know or may not realize, the filling process in most cavities is generally less than a couple seconds. So this plastic is flowing and this pressure is being sensed almost instantaneously. So that's the basic construction of the sensor. The type of sensors that we have to look at industry-wide are direct sensors, which are mounted directly in the cavity, indirect sensors, which are mounted typically behind an ejector pin or a stationary pin, or a third category is contactless sensor. And this is a sensor that's essentially bottomed out into the backside of the cavity using the cavity steel as a transmission source to get the plastic pressure felt onto the tip of the sensor. Each type of sensor has some advantages and disadvantages. The primary advantage of the direct mount is that it's right at the source of the plastic pressure. One of the disadvantages, it does leave a witness mark similar to an ejector pin on the part. In the event that that's something that we have to work around, we have some other options then. The indirect sensor mounts behind an ejector pin, as I described. It generally is very easy to retrofit into an existing mold, and so that's why these are extremely popular when we're looking at upgrading existing factories to get them into modern molding. And quite innovative design here is this contact-free sensor, where, as I described, if you have like a lens or any kind of surface that cannot have any blemishes or is so small that a sensor would not fit on its surface, this contactless sensor is great for micro molding, silicone, or even lenses where there's imperfections are not permitted by witness marks of any kind of pin. So just a recap kind of different types of sensors. In addition to them sensing pressure, we could also add a thermocouple to the tip of these designs, making it a pressure and temperature combination sensor. The direct sensors or the indirect sensors fit under the ejector pins and essentially have several different sizes that will accommodate virtually all types of installations, regardless of diameter of the ejector pin. The non-contact are seen here that mount in the cavity block, and then we have a sensor that actually could measure the strain of the steel outside of the mold. General installation of different locations in the mold. Cables, as you can see here, the single wire cable can be used in almost all applications, and it is a much thinner routing and is custom cut by you, the operator. You don't have to order it to the exact length. It's also then repairable on site based on the fact that there's only a single conductor in the wire. Coax options are also available in the event that the cabling is routed outside of the mold. Where we put the sensor in the mold will determine the type of graft that you will get. So the closer to the gate, you'll see a higher pressure, and you'll see essentially a filling portion of the graft, versus at the end of fill, represented here in the red line, which is a smaller pressure due to the fact that the plastic pressure is actually dropping between the filling point and the end point, because plastic is always curing as it's flowing in, and so you're losing pressure as it's curing. Even though it's only 1 to 2 seconds, this is amount of pressure that's also being lost. You might also see a temperature sensor, and this is what the output might look in the graph format, where you see the plastic coming in and the touches the sensor, and you have an instant response. Now, it's not going to be a melt temperature per se, but it's going to be a very good indicator that plastic has reached the sensor. Just a bit of a correlation of how plastic flows into the cavity and the associated graph. As soon as plastic touches the sensor, you'll get a movement on the graph, and as it's filling, you'll get a constant upward curve. The end of fill sensor here, noticed in yellow, you just get a little mark that the pressure is there. You don't actually get any pressure until you get a full cavity. And as soon as the cavity is full, that's when the pressure spikes up, because there's nowhere else for the plastic to flow but against the walls of the cavity, thus giving you the spike in pressure. Further along the timeline, you see the graphs will start to descend. That's due to the plastic curing. And as the plastic cures, it shrinks away from the sensor, it shrinks away from the walls of the plastic, thus giving you the cooling rate of how the part is actually in its cure stage. And finally, as the mold opens, there will be pressure is essentially back to nominal before the process started. So using this graph, we can use this to verify and correlate to dimensional results and capability studies, and the process monitor system can monitor independently from the molding machine the different process settings. Just another comparison, just showing you the difference between post-gate and end of fill. Post-gate sensors are really good for controlling different aspects of the process because it's closer to the filling point. End of fill sensors are really good for monitoring part quality, as it specifically is in line with correlation to the cooling process, which and pack and hold process, which allows for the dimensional stability to be maintained. So, as we talked a little bit about pressure loss between the injection machine, here represented at the top graph, and these are the different steps of pressure due to the plastic curing as it's being pushed through the mold and essentially setting up. But this is a typical graph you'd see for the different types of pressures. And this is why it's much better to be relying on cavity pressure than the molding machine's injection pressure graphs. You get a lot more intimate detail of what's going on in the part. And especially if you have multi-cavity parts, 1 cavity versus 8 cavity, you could see that all 8 cavities are being molded in the same manner. Or if you can detect issues with any kind of inconsistencies. Again, the correlation between the graph and different attributes in the part is listed here in this table. The process monitor, the Como Neo, is what these sensors are connected to, and it comes in a version of 8-channel, 16, and 32 channels. So you can have a variety of different connections to this monitor system. This is kind of a busy screen, but it's showing all the different influences, or all the different signals that can be captured and recorded on the Como Neo for process integrity. So you can have history of how it's been running, or troubleshooting, or process development. And you could see here briefly, the types of curves that are being produced from the cavity pressure sensors. You have the molding machine input can be graphed. You can have the temperature of the cavities. You get a whole snapshot of the entire cycle. And in this case, you have a timeline on the bottom. It looks like it's 0 to 13 seconds. And so you have a history being recorded here. Send again the correlation of the graph to the different types of product defects that you may want to prevent. With the monitoring system, you can choose to select what's going to be a good part and bad part before the molds even open. Represented by what we call this evaluation object here, the red and green box. If the pressure curves are in the box, that would be an acceptable condition. Looks like 2 cavities are under the graph, under the box, and so these are designated as not good parts. And so they would be separated by your handling equipment, whether it's a robot or a offloading machine. Control of the process is actually also introduced by the Comunio by determining when the switchover point is, so you could switch from fill to pack. The Comunio is equipped with both a manual and an automatic version that you, the user, can set so you don't rely on the molding machine's position switchover. You can use the actual cavity pressure to do the switchover. Another form of control that the Comunio offers is it can take over the hot runner controller tip temperatures if you're running a hot runner tool, and it will adjust the tip temperatures in order to balance the filling process. And it does that automatically on each shot with a onboard algorithm. Connecting multiple machines to a common system so that you could see the status of your whole plant is easily obtainable. We've got the software that communicates with the Comunio and then displays to a common network location that all the users can have access to see what the status of each process is, and then also go back in the history to however long you need to go look back. This is essentially plastic processing, and some of the basic and most used concepts within the system. So I appreciate your attention, and I will look for any comments after the fact in our chat box. With that, we're gonna hand it off to our next presenter.
Kyle.
I believe Kyle is on board.
Yep, I'm here. Just getting the screen.
Perfect.
Yeah. So Kyle Fisher, I'm gonna go through our assembly process control. So different products that we offer and some of the applications that we address with these products. So our BUs are assembly process control. So we have a complete joining portfolio. So it's everything from just single components such as sensors and amplifiers and process monitors to our servo press solutions, which is a complete system, to a complete solution, which would be our standalone smart stations that involve all the integration, everything done for you. So everything in the industries from automotive production, general manufacturing, medical device assembly, aerospace defense, and our customers are everywhere from the machine builders and integrators to the end users. And applications that we use these products in are joining, press fitting, crimping, spring testing, pretty much anything where you want to measure a direct force on a product that's either being put together with another product or being formed. And then we have a few different types of where we're just monitoring, or we have the closed loop systems. And then some of the customer characteristics are it's demand for components where they already have a system in place. So there might be retrofitting to where they're looking for a complete kind of turnkey solution that they can use either on like a substation of a line or in a lab, for example. There we go. So Mike already went over the piezoelectric effect of when you compress a crystal, it outputs a charge. So the advance of the Kistler piezoelectric sensors is that we have multiple varieties based on those different crystal cuts, but it allows you to have very small compact sensors that have wide measuring ranges. And so the other advantage too is since you have that wide measuring range and you have a very linear output from the sensor, it gives you rangeability, which is you can use, for example, a 50 kilonewton sensor, but it also comes calibrated at 0 to 5 kilonewtons and 0 to 500 newtons, so 100%, a 10%, and a 1% range with the same linearity and same accuracy for each of those ranges. So you can use one sensor for multiple applications, or you can oversize the sensor to make sure you don't damage it, but also get the resolution and accuracy down at the low end. And then the sensors have great durability because they have the stainless steel and you are compressing a rock. So you have long-term stability of the sensors that can last 30 plus years, 15 plus million cycles, and you never have to worry about damaging them unless you obviously are using them in the wrong way or submitting them to environments that are outside of their spec. So with these sensors, the best measurement is your direct measurement, so directly in line with whatever product you are assembling or testing. So then we have a couple other options too, which would be your shunt measurement, where it would be below in the, say, the steel underneath the part, where you're collecting, say, 60 to 80% of the force that is traveling through the part. So you can still correlate a good part versus a bad part based on that profile curve. And then the other option we have is with one of the sensors that Mike showed is the surface mount surface strain sensor. So you're measuring microstrain with it. So for example, in this picture in the bottom left, you have the sensor mounted on the C-frame here with one bolt. And basically it's measuring the microstrain of the flex in that steel as you're assembling the part. So again, you can either do a calibration on this to directly correlate your force with it, or you can correlate a good versus bad part based on the output of that strain from that sensor. So the advantage is that with the sensors, we have multiple options of where you can install them. And then also one other product we have with our sensors, we have torque sensors. So we have piezo reactionary torque sensors, but also we have our strain gauge rotational torque sensors like the rotor and stator format here in the bottom left, but also the flange and stator version on the right here in the bottom middle. So the advantage is that we can do, rotation just for in speed, or we can do rotation versus angle. And then again, with some of these sensors, we can do multiple calibrated ranges on them. So you can have an oversized sensor, but also get the actually down at a lower end as well. So some of the measuring chain examples. So as Mike said, all the sensors have to go to an amplifier. So some of the amplifiers that we have here in the top left are simple, analog output or digital output directly connected to your PLC, or for the analog, a 10-volt signal going to your PLC. So then we can also use those sensors and some of our process monitoring solutions. You can retrofit old hand press type stations, or you can go to our other process monitoring solutions and be able to do basically just any XY plot, for example. So you can do pressure versus time, like Mike showed. You can do force versus displacement, torque versus angle, force versus time, whatever the two components you want to plot against each other. And then lastly, as I said, for a full system, we've integrated the force sensor and the absolute encoder into the servo press system, which then still goes back to our process monitoring system. So everything is an integrated solution for you. So then going into the start of the process monitoring solution, so you have your sensor on the left, and then you have your process monitoring system in the middle. So with the process monitoring, it allows you to get better process transparency. You can do trend tracking and you have your traceability, but then it also allows you to have complete process control. So you can analyze every single part, link it with the serial number, and then be able to go back into your data that you collect with all the parts that are being assembled, and actually analyze all that data post-process if you wanted to look for variations in part quality or tolerances of the parts that are coming in from your suppliers. So where the production monitoring systems and the force sensors are all used. So we use them inline, end of line, and also offline. So again, like you see at the bottom left, you have your force sensor, for example, and a displacement sensor going to our process monitoring system. So if you're doing force versus displacement, so you have a bearing going into bushing. So if there's any variance in either of those parts, like example on the bottom one, you're going to get a bad process curve from the windows that you set. So the advantage of the not actually using the process monitoring system versus just using the analog or the digital amplifiers that the PLC is doing all the basically determination of good versus bad part. You're getting more data that's being stored and collected. You're also getting immediate like visual and digital feedback. So you're actually seeing the process happening, but then you're also having that signal, say over field bus to your PLC, also storing or analyzing and determining if that part is good or bad based on some of your own criteria as well. And then it's a simple interface. It's easy to set up, easy to use. It's basically, if you can learn how to set up an iPhone within an hour, you can learn to set this up in an hour also. And then also your traceability, storing all your CSV files up to 5,000 on board, but then it's also outputting every one of those CSV files every single cycle. And then you can also send them to different folders in your server based on, either shifts or batches of parts that come in. So you can basically organize that data on your end in your server as well. So then some of the options that we have for the Maximos, we have our standard one, and then we have a medical version, which is your Part 11 compliant for your data export and your data export, any user changes or login changes that are done to the unit. So it's FDA and compliant. And then we also have our Maximos BO, which is our kind of basic level unit. If you're looking to like retrofit a station, you just want some type of visualization into your process, but you don't need all the bells and whistles, say, of the one on the left. But depending on the application, obviously we can go in, and depending on what you're trying to do, we can recommend the best solution for you. So as you can see here, some of the things you can do for a simple like press fit application, like a snap or a click feature on a part. So like on the right side here, you have your curve with your evaluation windows that you set up based on what your perfect curve would look like, for example. So all these windows are determined to be pass or fail based on the criteria that you set and where you set them. But also you can, say, run calculations to determine like a snap force of that part, which you can see here is number 2. And then also you can set up, with all these features that you're seeing live, you can set up your own process value table here on the left. So you can basically pull these critical points, so such as like max force applied, excuse me, the click force of the calculation, for example, number 2, the device finish height, where it actually ended displacement wise, and then your furthest displacement along the curve. And then, for example, number 5 is your evaluation units. You can basically also output those in a CSV file if it's determined good or bad, or okay or NOK. And you can see that as it's happening. And then once that process is complete, as soon as it ends, before like you're even ejecting the part, all that data is already being exported out to your server. So basically you can set up to 10 of these windows as a standard. We have a feature where you can do up to 20 of these windows per curve. But the advantage is that you can actually keep critical data in a format like this on the left versus sending the entire curve data over CSV to your server if you don't want to keep as much data and you just want the critical components. So some of the applications where these sensors are used would be card switch testing or testing of probes for semiconductor type applications, or check valves. Just any type of simple assembly where you just need some type of force feedback to know that your part is being tested correctly and that your process is being verified. So next, I'm going to go into the joining systems, which is basically taking your sensor and your XY monitoring and putting it into a complete package for you. So the electromechanical joining systems, again, used for a lot of the same applications that the sensors are used for, but you're getting the complete control over the process because you have the electromechanical joining system that's you're telling it where to move and what speed to move. So used in every industry from automotive, the classic ICE engines, transmissions, and turbochargers to electric drive units and batteries, all your pump, steering, and brakes, and again, your medical insulin pens, white goods, power tools, electronics, any type of assembly or switch testing that needs to be done. So the advantage with our Maximo system is it's a common family. So when you know how to use one, you know how to use all of them. So on the right would be kind of what we were using or what I was showing earlier, where you have the Maximo system and your sensor with some type of actuator, be it pneumatic, air oil, or a manual hand press, for example, to where you're using the joining system, which you're still using the same process monitoring tools, you just are now in control of the motion. So it gives you the advantage of flexibility and for your press fit operations. And then it also makes it a lot easier to install because there's no configuring of anything. There's no putting multiple components from different suppliers working together. There's lower maintenance because all you have to do is essentially grease the unit. And then obviously you have lower energy consumption if you're using electrical systems versus using air over oil or pneumatic. There's no pumps, there's no leaking oil, there's no air pumps, there's no fluid disposal, no seals breaking and stuff leaking and cleanup and all that other stuff that comes with it. So the elements of our joining system, our servo press system, essentially you have the press module, which has the motor, the force sensor installed, and then the absolute encoder installed. The IndraDrive, which is the servo amp, along with the safety zone box, so all your safety wiring, so your e-stops or your light curtains or anything like that would be wired in your safety zone box. Or if you have a safety PLC, for example, you could wire that directly into the safety zone module. And then you have your MEM, which is the brains of the operation, which is the Maximo software, which is installed on here. So it's the measurement and evaluation module. So this has all your information. This is where all the data is being collected and stored. All your communication is being done to the PLC. And then a display, which is just a display. You can always use a PC, and then we include all the cables as well that come with it. So we give you a complete package that's calibrated and all together and set up together. So when you get it, you don't have to do any work internally to our components, except setting up your press sequence of what you actually want to be pressing and what the assembly process will look like. Which is what we'll go into here. So you have your base layer products up here at the top, the Maximo system, the drive, cables, and you have your servo press. So bottom left is where you have essentially the basic setup program that I would say of assembly process. So we have a bearing going into a bushing, for example. So you want to start your measurement process. As you can see, you have an idle stroke before you come in contact with the part. The joining stroke where the two parts are being put together, say pressing to an 800 Newton force. You don't want to measure any more of the curve. You retract to your home position, that's your sequence. So as you can see, you have your graph of force versus displacement, and then here's your good part being pressed together, and this is what your curve will look like, for example. And then you have the windows that I was talking about that are set up. So you can see that the curve goes through the windows and you have a good part and you have a good process. So now if you have a variance in your bearing or your bushing, for example, you could get what the red line would cause, and you have a bad part where it's missing one of the windows and it's coming in contact with the part at a later distance. So therefore you can determine live that it's a bad part assembly, and then you can kick that part out or do rework on it or whatever the next step would be for an okay part. And so the advantage of controlling the process with the servo presses versus using just the monitoring is that you actually are controlling the process. You're controlling the speed at which you're assembling the parts. You're controlling the forces that you're applying, and then you can therefore reduce your cycle time with different speed settings because you're not moving only at one speed. You don't need to come into large or a fast contact with the part, for example, like on the right where you get a spike if you're only moving at one speed. You're hitting the part harder versus coming to the part slowly and then actually joining the two parts together, which gives you less NOK parts versus more NOK parts. And the main advantage also is too, it's that you have control so you can adjust it. Where if you're using any type of other actuator where there's no kind of speed or control settings really, it's just going from A to B at whatever speed that is. So you have one element of your process that you can't control. Therefore, you can't alter that when you have your different parts coming in. So again, some of the other applications that we use the servo press systems with are so transmission assembly, also engine assembly, valve seat and guides, all your fuel, oil, water pumps, things like that. Also chassis assembly, electric power steering, or your sensors that are used for the radar on your cars for the blind spot monitoring and things like that. Also, again, general industry from medical device assembly, auto injectors, electrical assembly like PCB boards being pressed into plastic housings, White goods, for example, the spin tube for like the old school washers that's in the middle that you have to stuff your blankets and stuff around. And then also other industries like spring testing, for example, this for the elasticity of the spring. So again, the benefits of using the ServoPress systems. So one, it's reduction of CO2. A lot of obviously global push to reduce carbon emissions from corporate push usually, but you are reducing overall CO2 output as an advantage. And then two, you're also reducing your total cost of ownership. The cost of using electrical joining system versus a hydraulic it's 10% because there's no pump. The only thing you're using is electricity. There's no pumps running all the time. There's no other oils that need to be shipped in and out. And there's less maintenance that needs to be done on that product. And then also 3 is the reduction of NOK parts because you are controlling the process versus just running, say, a hydraulic actuator at 1 speed. So the portfolio we have, so we do everything from 50 newtons all the way up to 700 kilonewtons. So depending on what the application is, we have a fit. For example, the low force range is the NCFT, the top left one here. And then if you're chasing cycle time, for example, the NCFH has advantages because it has a hollow shaft motor design, so we can achieve much higher acceleration and deceleration speeds along with stroke speeds with this one. If you need, say, a custom stroke length or very high forces, our NCFN model is the one we would go with. Or if you need, say, an economy model where you're trying to compete with what you already either have on the floor, your customer, for example, is wanting to use air over oil or pneumatic press. We have the NCFE, which is much more economical as far as price-wise. It obviously has more limitations on what it can do, but if that's what you're competing against, we have that option as well. And then what I'm going to go into next is what we're coming out with, officially launching next month. We're calling it NCFQ. So Kistler partnered with Linmot, a Swiss actuator company. So basically with what customers were doing before, maybe using Linmot, they were doing all the programming in the drive, and they were hooking up our process monitoring systems to it with a force sensor, for example. So now what we have is the Linmot drive will communicate directly with our Maximos NC system, just like our ServoPresses do. So you're setting it all up just like a step table. So then it's for low force ranges from 0.1 to 500 newtons, in stroke from 60 to 700 millimeters or so. But the idea is the speed is much faster, so up to 5,000 millimeters per second, which standard ServoPress type design can't achieve. So with these, they're also ISO 4 cleanroom certified, which helps getting into certain applications that, say, a ServoPress with grease or things like that are evident isn't possible. And then with this also, we've come out with a new product the past year, our ICAM B. So it's basically just a simple charge amplifier. But what it can do is with this option, we can basically hook a force sensor and one of our accelerometers to it, and then allows you to basically do acceleration compensation. So as that Linmot actuator is moving up and down, you don't have to adjust speeds to slow it down to make the curve look more correct. You can basically cancel out all that noise of that large tooling moving up and down. So for example, using this with insulin pen assembly, there's usually it's high speed, obviously, because they want to make as many parts as they can as fast as they can. And the tool weight's very heavy because they're doing it for multiple products at the same time. So there's a lot of dynamic forces that are changing or going on from it moving at high speeds constantly. And the thing is that the noise essentially can be higher than the actual values of the click of the parts of the insulin pen being put together. So the only solution was to actually slow it down before you hit the part, but then that starts causing higher cycle times and causing more mechanical stress on the machine because you're having to slow down and do more alterations to the mechanical structure of it. So with this acceleration compensation that we have, so basically the curve on the left is what it looked like before. So their travel time was 0.4, their 0.75 total seconds for each cycle. So with the acceleration compensation, we were actually able to knock that 0.4 seconds down to 0.15 seconds because we can remove all the inertia from the acceleration. So you can see the curve on the left is what it used to look like, and then when you add the accelerometer with the ICAM-B, that's what the curve on the right would look like. So the quality control department was a giant fan of this because the data that they're actually seeing to assemble the part, say in a slow pace environment, is what it's actually looking like on the production floor. And then lastly, taking all those things together for a complete solution that we provide. So call it the Smart Single Station. So basically we're using our server press systems, our control, all our know-how from Kistler, all the applications that we've worked on in the past, and building a complete station that we can supply to you for either product development or kind of offline testing, things like that. You could essentially use it as a part of your assembly line in a way, but it's not really our main idea to compete with the machine builders, for example. It's more of just to offer a complete package for, say, you, the customer, buying a bunch of components and doing it on your own. So one example that we've done with this is a customer in Europe for developing new packaging for coffee capsules that are more sustainable, different materials, things like that. So they wanted to basically do this on their own, and then we offered the entire package for them trying to build it in-house and giving them design ideas or different specifications and things that they could try. So they ended up going with our solution. So it's just again, it's not full production. It's just a simple lab type press that they can do development and design on. So again, the main thing is that we offer everything from just components so that you can retrofit stations, or you just need simple force first time feedback to an amplifier, or you want to just monitor the process. You already have one in place. You want to add a sensor and a displacement sensor and run it back and get a live XY feedback and get some data output. Versus, say, what you have, maybe you don't have anything at the moment, or you're using a PLC to do the analyzation. So with our systems, you can get much higher data analyzing rates, so like 5 kilohertz up to 20 kilohertz on some units for analyzing your process curve. And then again, taking all those components, supplying a complete system that you can use for your assembly process, and then finally a full solution that you can use also as well with all the know-how of everything that Kistler offers. And that would be it for me. And then next, I will pass on. And again, any comments or questions, you can please throw them in the chat and we will get to them. And thank you.
So, thank you, Kyle. Sure. Good morning, everybody. Hopefully you guys can see my screen. My name is Hernan Hernandez. I am the applications engineer for our vision inspection business line. So a little bit different than what we've previously been talking about. Now we're going to go into a little bit of the machine building instead of component-based solutions, but we're still doing the quality monitoring using our solutions, right? So Kistler itself, Kistler itself is building the machines that you see on screen. I would say that the top three that you see on the top are standard solutions. These are typically configurable and modular enough to handle different applications, while the bottom three machines are more one-of-one solutions specific to the application. So certain inspections require, let's say, a robot handling solution that would be specifically to that part. That would be the bottom three solutions. So in this case, we're going to be talking about the standard solutions that you see on the top. So where our systems are, we're doing quality monitoring in line, so in the production process, right after the metal forming. In this case, the stamping line, you would see the system directly right after the stamping process, and we're inspecting 100% of the parts that are coming out of the stamping press. We're doing dimensional inspection. So some metal form parts have, let's say, strict tolerances, and we could do in 100% inspection of these dimensional features. But we could also do surface inspection. Let's say you have certain stains or scratches on the surface level. We would use a color camera for something like this, right? We could also do a 3D measurement, to now do a Z measurement. And then directly after that, you'd see that some customers are also wanting to have traceability of these parts. So we'll build this separate machine, which is a laser marker. So now we're etching 100% of the parts with an alphanumeric code, a QR code, a DMC code. So these are the solutions that Kistler offers to our customers. And how that looks is, here's a rough video. Hopefully it transmits well. So this system here, we're using our camera systems. This is our interface. This is what the user would see. A part is now flagged as a non-compliant part. The part is then fed onto what we call our stamping solution. So the part is stamped out of the reel because we want to eliminate any escape features or any containment issues. So the parts are removed out of the strip. Because some customers have a downstream process that does not allow a gap to be in this reel, we're going to re-weld the strip back together, eliminating the gap that was left behind by removing the bad part. We're doing this all in real time. When the press is running about 1,000 strokes a minute, this is the solution that Kistler is offering. And what Kistler is the interface itself. It's the software, right? We do use third-party vendors for our cameras, our lensing, but the real Kistler solution is the software, right? What is grasping the data, what is collecting this data, what is illustrating this data to our customers. And here is an application example of an alphanumeric code on the part itself. With this laser marker, we're limited to 1,000 parts a minute. And then I'll showcase some of the applications that we've done these past year. So MedTech, we're pushing heavy MedTech for our vision inspection solutions. This was an application that was here in the States. We were able to integrate this 621 system with the 3-camera solution to do strictly dimensional measurements. And we were able to do this for speeds up to 500 strokes a minute. And these are medical needles that are entering into the body. So as a critical component that needs strict dimensional inspection. And then another application that we just realized in Denmark, this was for another reel-to-reel application. These are the spring compressors that are inside the insulin pen. And again, we're doing dimensional inspection, but something that was unique to this application was that we're also doing a surface inspection to see if there's any contaminants on the plastic that's overmolded here. Some of our capabilities that we can do within our vision solutions would be, we could do surface inspection, right? So surface inspection for capturing stains or contaminants on the surface level. So you could see that with one camera, we're taking 4 different images, and this eliminates the need to have multiple cameras just to do multiple surface inspections. So we can capture contaminants. We can also capture scratches or nicks on the surface level, is what you see there highlighted in red. But we're also in the overmolding world, right? So we would integrate a vision inspection solution right before entering the molding machine based on the results that our imaging system shows. If there are any damages to these contact pins here, then we would communicate with the molding machine, tell it, hey, there's damage to this reel, index to the next set to prevent any tool crashes. But we would also do a post-overmolding inspection to make sure that there's no short shots, no flash, or any bent pins due to, let's say, tool wear. Here's an application for short shots. So here our system was able to capture short shots, and we're talking about micrometer level short shots. We are also able to capture scratches that were a result of tool wear during the molding process. In this application here, we're illustrating slugs, right? Top left, you see a slug that was caused by tool damage, but we were also able to capture flash on the contact pin. This is the key feature that would make the contact for this semiconductor. And then another semiconductor application where we're capturing another surface inspection, so a stain on the surface level. But what is unique is that you could see that even the center plate orientation was a defect that we were able to capture. So the center plate was not in the correct orientation, and then this part would be flagged as a non-compliant part. And for singular pieces, now we're not talking about reel-to-reel. We have the 121 solution, so you would feed singular pieces into our machine. Here you'd see that we're making an inspection on turned parts, and we're using a mechanical feeder to feed the parts into our imaging system. So it's a bowl feeder that would orient the parts and then feed them onto a linear conveyor. The linear conveyor would then feed it onto our camera stations. You can see that some of the parts are blowing back into the bowl feeder. That's because the orientation is not correct and or the parts are placed incorrectly. And so now the linear conveyor will feed the part onto our camera station. Our interface showcases parts counter, right? So you would see a total count of parts being inspected, uh, parts counter for good parts, and a parts counter for non-compliant parts. So here is our camera station. You see that we're using a two camera solution, and as the part is free falling on this rail, on that small 3-inch window is where we're capturing the images of each part. Then based off of the results of our imaging system, we would sort into either good bin, where all the parts are good in this bin, or a non-compliant bin, so isolating the bad parts. There you'd see the mechanical actuation of this divider that's separating the non-compliant parts. And what's neat about this solution is if you have a family of similar parts, it's very easy to do a changeover and switch over to the next set of parts to do inspection on multiple family of parts. But part of our capabilities are also 3D measurements. So as I spoke earlier, if we want to do a Z measurement, let's say a flatness measurement or a coplanarity measurement, then we would use a laser triangulation to do Z measurements. And here I will showcase to you guys a high-speed inspection. This is for the fastener application. So now we're moving into a 800 series. So this is really ideal for high volume throughput. When throughput is required, then we would use a system like this. So it's a glass table, and we're doing speeds up to 700 parts a minute. See that we used a custom feeder solution here with the belt-driven feeder. And because the customer required a high throughput of this inspection station, we're using multiple channels to feed into our glass table. So what's neat about the glass table is that since it is transparent, we are able to do inspections on the top side, bottom side, side view. This gives us more versatility in the angles that we can do inspections. Here you could see a live image, result image. So and you could also save the images for the non-compliant parts. If you want to come back and see why the parts failed, you could cycle through the bad images. This customer wanted to have us integrate a packing station. So the packing station that you see there is also a solution that we delivered to this customer. Here we're indicating how we're using the high pressure nozzles to blow the units into the correct bins. In this case, you see that red indicator that will blow the parts that are non-compliant into its individual bin. With the glass table, we have the ability to have up to 4 sorting bins. Let's say there's a second or third priority where you have parts that could be reworked, let's say for a plastic component, then we can, based on that feature, we can, if that fails, then we can isolate into it, so let's say a rework bin. And then lastly, what I wanted to touch base on was integrated solutions. So let's say you have an existing assembly line or existing production line, then we could also integrate our solution into this existing production line. Here you could see our camera stations being integrated into an existing assembly line. Similarly, here, let's say you're doing a molding process and you want to do post molding inspection, then we're working with the end of arm tooling to present the parts to our camera station. In this case, we were doing a coplanarity measurement and to measure this and see the effects of the cooling post molding process. So, thank you guys.
Thank you, Hernan. I will carry on here. Let me go ahead and pull up my slide. Thank you, Hernan. Thank you, Paul. So carrying on from Hernan's conversation here, my name's David Allen, and I cover 2 hats really with Kistler. First off, I'll go over the sensors, the optical sensors that we use primarily in stamping, punching, forming, and automation technology that kind of pair nicely with the products that Hernan was just talking about. So in this image, we kind of give an overview here of an entire stamping process. The products you see in 7 and 8 are what Hernan just covered for you, and I will be going over the 1 through 6 process in the actual loop control and stamping machine. So here's a quick overview of some of the products, the optical sensors that we offer. You'll see fork light barriers, which are the most common that we offer. A variety of different setups, with them being fork light barriers. We offer on the right-hand side split light barriers. We have some unique solutions with cleaning nozzles, blow-off valves here for oily or dirty type environments to keep the nozzle of the lenses clean. We have these fork light barriers that are used for double sheet control, double thickness control and detection, where you can mount a piece on the top plate and we can detect if it's fully closing, clamping down here with the bottom plate. We offer them with, this is a digital output. This would be a similar idea with an analog output, so give you a little bit more control there. We have frame light barriers for ejection control, making sure that a slug has been properly ejected. The loop control sensors for making sure your feed rate is correct, not getting too tight or too loose, and then some contact sensors for presence control. So here's an overview of a typical die, typical stamping die that we would maybe find some various positions to put these sensors in. And then I'll show you here a blow-up view. So like I said, we have optical sensors, the fork light sensors that can be used maybe for rivet detection or position control, making sure that the strip is coming through and properly positioned before we stamp. down on it to make sure that we don't damage the die. So in a typical feed control application, we have a sensor, a fork sensor here that's monitoring the strip as it comes through. Typically we'll have some kind of indicator pole, and we're counting those positions, making sure they're properly lined up before we stamp. If there's any misalignment going on, then the laser doesn't, the optical light doesn't fully connect, and then we can stop the machine. So here's an example of a strip moving, in this case left to right. We can see the strip 14 millimeters apart. We have some detection holes, and we count them. Our sensor is here on the exit side, and we're counting these holes as they go through. So we can use them. Typically they get mounted on towards the end, so we get better control, better idea of what's happening in the process. And if there is any kind of misalignment happening inside, that will cause misalignment at the end of the strip as well, and alert us that there's a problem going on. So we can immediately stop the machine, protect the die, protect the equipment. Now our sensors are used a lot in high speed applications. One of the benefits of these is that they can do 4,000 samples per second. And so we'll show you here in an example on a high speed Bruderer stamping machine that we're doing an example of 2,000 strokes per minute. So let me play this here for you. And here's the operator starting the machine. We have a loop control sensor that's detecting this loop as the strip as it's coming off the loop, the reel, and it's coming into the machine now. And as it comes up to speed, you'll see an example. We don't have the sound playing to protect your ears at the moment, but it sounds quite impressive as we're hitting the high speeds. And the strip is running through the process. Now we're detecting every single time as it's getting positioned, getting lined up, and getting stamped. And in just a second here, we don't have to see the whole video, but you'll see the display showing that we're achieving at least 2,000 strokes per minute. And I think we've even had some machines go faster than that since this video was taken. So there you go. So additionally, our sensors, I mentioned the ejection control sensors. These are frame barriers. So we have a frame that can be put underneath to make sure that a slug is properly ejected. If the slug is not properly ejected, it could be jammed in the die itself in the stamping process, and then as you come down, you could definitely damage the equipment. So we want to make sure you're properly ejecting and that you're clear for the next stamp. The frame barriers here, we have crisscross versions as well, where the beams are crossed from each other, and we can detect down to less than 1 millimeter slug that would be ejected from the machine. So in addition to the stamping process, they can be used in a variety of other applications. Here we have a split light barrier being used for presence control. The fork light barrier is being used for presence control, so we can detect this bolt here as the plate moves up and down or moves into position. Something's moving into position. We can detect if a feature is present or not, and that can alert us if something is properly positioned or not. Additionally, we can use the ejection frame sensors for counting parts. So if we're filling a bin, if we need to fill a bin to a certain number of parts, we can use this as a part counter, and once the bins are properly filled, then they can move on. And we can use a split light barrier as well for presence control for those bins to make sure that they're being properly routed afterwards. A wide variety of different applications as well, so it's not just limited to stamping. So like I said, it's a very robust sensor. It's a very high speed sensor. We can detect very small parts, and we have the ability to keep the lenses clean with the blow-off valves. So that covers that one. I will switch my hat here for just a second and go over some of the other solutions that we have at Kistler. So in addition to those topics that we've covered, we also have sensors that we use for monitoring tool wear, tool breakage in CNC and metal cutting type applications. So Kistler's been around for a long time. We've really done well in the research and development for cutting and machining tools. So in research and development for CNC machines, CNC tooling, coolant development, that kind of stuff. I'm not going to go into that detail today, but we have that information if you're interested in it. but we're really expanding into the tool monitoring side of things. So understanding tool wear, tool breakage, spindle health, that kind of thing. So here's an example of a thin-walled membrane that we machined. And you can see when we used, let me put my pointer back up here, just one second. When we use a brand new tool, the forces are low and we get a nice clean cut, nice clean signal. As the tool starts to wear out, maybe by the 100th part or so, our forces have increased quite a lot and we're getting a noisier, not as clean cut, right? So we can detect by setting a force limit here when the tool is starting to wear out and when it might be time to replace it. So similar idea here, first part, nice low force, nice clean cut. And we can see as the tool starts to wear out, in this case, maybe 5th part or even 10th part, how we're already seeing a dramatic difference in the force curve as we do this. So we have a wide different ways of doing this, but here's one of our software solutions where we're looking at a new tool versus a worn tool in the time domain. We can also look at this in the frequency domain and see the types of frequencies, or maybe with a high pass filter being applied to it, a new tool versus worn tool. So it's very quick and easy to identify when tooling is wearing out. We have lots of different solutions for this. I won't go into all of the details today, but just know that we have, depending on your specific application, there's a wide variety of ways to do this, from software packages and the Maximos that Kyle covered, to direct communication with the machine PLC. We have wired and wireless solutions. We have instrumented tools, tool holders, or ways to monitor directly on the machine spindle, all the way down to force sensors, strain sensors, vibration sensors, pressure sensors, all depending on your specific type of application. So we're really using some of our standard off-the-shelf sensors that we have and taking them into the Maximos solution so that you can monitor it remote or independently, or into one of our amplifiers to send analog or digital signals into the PLC. So here's an example of a surface strain sensor that's still piezoelectric, but it's measuring just the flexion in the structure itself. So we have it oriented in 2 different ways. We're coming across cutting material and using a Maximos to monitor that signal. So it could depend on your specific situation, your setup, where we would mount something and what the best solution would be. But what we're noticing is you've got the tool down here, but we're picking up the force up here. So the force is being applied on the tool, but it travels through the structure itself, the rigid, stiff structure itself, and we're able to pick up that tensile force with a strain sensor in this application. Here's one where we used a similar strain sensor and compared it to one of our high-end rotating research dynamometers. So with the research dynamometer, we clearly get a very clean signal, a very detailed signal. We could zoom into this and see specific tooth and tooling, the insert engagement, tooth engagement with the material. Whereas with the strain sensor, we're able to see a basic idea of low force, new tool, higher forces, worn out tool. So it's not going to give you the same level as an R&D solution, but it can show you that trend for sure. Here's an example in a drilling situation where we have a drill that may be coming down here and drilling on a part. So the force is being applied down here, but the force travels up through the structure. The structures themselves are very rigid, and that helps us. And the force shunt gets sent through a force washer. It looks like this washer we have up here. But we tightly mount this to the frame itself, and then it's able to pick up those forces from the drill tip itself. So we can see in a Maximos a new drill and what those forces look like, and a worn drill and what those forces look like. One last, a few more examples that I have. A force sensor with a strain sensor with a dynamometer. So we can see that we have a few different solutions that are all showing a very similar trend. So multiple ways to measure this, and it really depends on your specific setup, which one would work best for you. And then one more that we have is in a lathe application. So lathes can be challenging with the rotating turrets and cabling. So what we've done is, here it is with a dynamometer. But what we've done is removed a bolt on the actual frame itself, the structure itself, and put a slimline force sensor under the bolt. So now we're out of the way of the rotating turret, and we're able to pick up the forces that transverse through the spindle head unit itself. So this is a bit crowded here, but just to show that we have a wide variety of different applications, where we would mount them, what sensors we would use. But if you are interested in monitoring for tool wear, tool breakage, spindle health, vibration, that kind of stuff on any CNC type machine, we have lots of different ways to take a look at it depending on what you need. So please feel free to send a note in the chat if you have any questions, or we can reach out to you directly on that one. So thank you for your attention.
Okay, thank you, David. That was excellent. And thank you to all speakers today for sharing their insights. We hope you, the audience, found this information valuable. And I hope that you get a clearer picture of how in-process monitoring and control can support your manufacturing operations. Unfortunately, we're out of time for live questions, but if you did submit one in our chat box, we'll be following up with you shortly by email. And on behalf of the entire Kistler team, we truly appreciate your time and attention today. Like I said earlier, we'll be sending out the webinar recording shortly, and we encourage you to reach out if you'd like to continue the conversation or discuss specific applications. So thanks again for joining us today, and we look forward to hopefully connecting with you soon. Have a great day.